So in previous lecture, we started the topic Laplace transform. So Laplace transform we usually find for the functions which are defined on the positive real axis. That means the function is defined for non-negative value x, right? So it is defined on 0 to infinity. Whenever such a function is given, we will define Laplace transform of that function, which is defined to be the integral e power minus st ft dt, where s is some real number. And we define the Laplace transform whenever this integral converges. So in previous lecture, we did not discuss when the integral converge, but we will state one criteria in this lecture that for which type of functions this integral always converge. So, so this is a formal definition of Laplace transform. Whenever the integral is finite number, we define it to be the Laplace transform of f, and this quantity depends on number s. So therefore, it is a function of s also, right? So every Laplace transform of function is a function of s variable, and in this case, we will write f of s is inverse of f function, right? So this notation we'll use. So first of all, we discuss Laplace transform of any power of the t. So we know that polynomials are functions in terms of x power n. So what is the Laplace transform of x power n? So that is what we found, that Laplace transform of e power n is nothing but n factorial divided by s power n plus 1, right? And this is true for all non-negative integer n. Yeah, so in particular, we have also found Laplace transform of one function, that is 1 divided by s. Okay, and then we define Laplace transform of e power at, that turns out to be 1 upon s minus a. Laplace transform of cosine at is a divided by s divided by a square plus s square, and for sine function, the Laplace transform is a divided by a square plus s square. So all these formula you need to remember the standard functions: e power 2x, e power 3x, cos 2x, sin 3x. What will be the Laplace transform? These are the standard examples. And then we discuss first shifting theorem, that says that whenever the function ft is given, and if we know its Laplace transform, then the Laplace transform of f of Laplace transform of e power at ft is just, we need to substitute in the Laplace transform, instead of s, we need to substitute s minus a. So we'll get the Laplace transform of e power at into ft. So whenever we have this type of example, we can solve using this theorem, using the first shifting theorem. After that, we discuss the derivative of the Laplace transform. So whenever we are given the Laplace transform of some function ft, then if we differentiate, we get minus derivative of the Laplace transform with respect to s variable. Right. So whenever we have a function multiplied with t, and we know the Laplace transform of f function, we can find Laplace transform of t into ft using this formula that says that we need to differentiate the Laplace transform of f with respect to s variable and take the negative sign. And the same formula we can use n times. So one example, we discuss t into sine at. We know what is the Laplace transform of sine at, and that we use to derive the Laplace transform of t times sine at. Okay, so that is what we discussed so far, and you can see that whenever we discuss Laplace transform of function, we also discuss the inverse of the Laplace transform. So by looking at function of s, we can also find out for which function that is the Laplace transform. So this formula, if we look at that, we can see that in the denominator it is s square plus a square whole square, right? So that means it is a kind of derivative of the term 1 divided by s square plus a square. And then we can guess that for this type of function, we have two formulas, sin 80 and cos 80 of this form, right? So for cos 80, we have s divided by square plus a square, and for sin, we have a divided by a square plus a square. So therefore, this, if we have this formula, then we can guess that it is a derivative of either sin 80 or cos 80. Yeah, so we'll see such examples whenever we'll discuss solution of initial value problem. Maybe today we will discuss such example. But first of all, let us discuss the criteria when the Laplace transform exists. So this statement is existence of Laplace transform. So earlier we discussed that we only need that ft to be integrable function because we are integrating it from 0 to infinity power ht ft dt, right? But in fact we need something more, that is, suppose we have the function, let ft be a function which is piecewise continuous and yeah, so piecewise continuous, where piecewise continuous on every finite subinterval. In the range t greater than equals to 0. So that means over the positive real axis, if you take any subinterval over which ft is piecewise continuous, and ft also satisfies the condition that m times e power kt for every non-negative t, right? So this says that modulus of ft is some constant times e power some constant times t, right? Where k and m are constants. So here constant means they are real numbers, and since we are taking modulus of t less than equals to m times this function, that means m is a non-negative number, right? So then what can we say is, we, in this case, Laplace transform exists. Right. So the simple example which we discussed, the first example, that is t power n function. So let me go to that example. We found that Laplace transform of t power n exists, right? So what does that means? That means that for which value of k, if we take ft is equals to t power n, then for which values of k the Laplace transform of t power n is convergent. So we need to compare t power n modulus of t power n, because t is non-negative, modulus of t power n is t power n, right? Because t is non-negative. We are integrating over the interval 0 to infinity. So now what m and k we can find, so that modulus f t is less than equals to, you can compare it with e power kt, right? So if we take, for example, if we take k to be some number 1, let us say, right? So suppose we take k to be 1. So what we get? We get e power kt is e power t, and e power t is what? We know it's series expansion 1 plus t square by 2 factorial e power n by n factorial and so on, right? So e power t has this Fourier series, this power series, and using this power series expansion, we can see that we can bound t power n as, so t power n is in this term, right? So if you want to write t power and t is non-negative, that means e power t is bigger than this term, this particular term, right? Because t is non-negative, and that will give us t power n is less than equals to n factorial times e power t, right? So what is this number? This is m basically. So we have written t power n function. We have shown that t power n function is of this form for constant k is equals to 1. So that means the integral converges for s greater than 1. Right? And for s between 0 and 1, we can use directly the definition of Laplace transform. And in fact, we have shown that it converges for s greater than 0 by directly applying the definition, right? So the directly definition, we are getting the Laplace transform exists for s greater than 0, and by applying this theorem, we are getting it converges for s greater than 1. Okay. Yeah, but here in particular we chosen k is equals to 1, but we can try if we can do apply this theorem for k is equals to 0 or not. So that you can take it as an exercise. So this theorem is very useful whenever we have a function which is bounded by e power kt. We can always find its Laplace transform. So this condition is used to find the Laplace transform of the derivative of function. So if we have ft is continuous function satisfying that it is bounded by e power kt function for some k, and its derivative is piecewise continuous on every finite interval in the range t non-negative. So whenever this existence of Laplace transform is satisfied, and in this case, we have assumed that the derivative is piecewise continuous, right? In this case, we can find Laplace transform of derivative function. Laplace transform of f dash exists and it can be given as Laplace transform of f dash is s times lf minus f0. So the proof is very simple, just application of integration by parts. The Laplace transform of f dash t is defined to be 0 to infinity e power minus st f dash t dt. Right, we are finding the Laplace transform of the derivative of function f. So if we apply the integration by parts, we get e power minus st as it is. Integration of f dash is f. Limit is 0 to infinity minus integral of derivative of the first function, that is minus s times e power minus st. Integration of second function, that is ft dt. So now we can see that this function is nothing but this formula is nothing but Laplace transform of ft function times s. And when we substitute here, so let us assume that s is positive. So let us assume s is positive, or even if that is greater than some positive number. Yeah, so what can we assume is a is positive. So k is positive and s is greater than k. That means s is also positive, and whenever s is positive, what do we get? We get, when we substitute here t is equals to infinity, that term will become 0, and the other term is when t is equals to 0, so e power minus st is 0 times f of t, and f of t is at t is equals to 0, it is f of 0. Right, so first term will be 0 because if s is positive, and the second term is s times integral of the Laplace transform. So this formula is very useful when we'll solve the initial value problems, because we need to find Laplace transform of derivatives, right? Because differential equation involve derivative of functions. So as an application, we can find Laplace transform of the second derivative also. So what is Laplace transform of second derivative? So first we will apply it for f dash, right? So f dash we can write as derivative of first derivative. Second derivative is derivative of first derivative. If we apply this formula for f dash, we shall get minus f dash 0 plus s times Laplace transform of f dash, right? And then again we'll use the same formula for f dash. We get plus s times minus f0, right? Laplace of f dash is minus f0 plus s times Laplace of f. So now we can simplify this. So what we get is s into s, that is s square times Laplace of f minus s times f0 minus f dash 0. So now you can see that the terms which are coming is in terms of f0, f dash 0, right? So therefore we can see the connection between initial value problem, and in general, if we differentiate the function n times, so second remark is regarding the nth derivative. So Laplace transform of the nth derivative. Now we can guess what will be the formula. So formula will be s power n times Laplace transform of f minus. So here second derivative, the term we have up to s power 1, right? 1 less power. So here now we have nth derivative. So the term will be starting from s power n minus 1 times f0 minus, so all terms are minus here in this part. So the second term will be s power n minus 2, first derivative at 0, so on. Last term will be nth derivative. Yeah, so last term doesn't involve the s term. So what we'll get is the derivative of the function n minus first derivative of the function at 0. Right. So using this formula, we can guess the nth formula, nth derivative formula. Yes. So let us see one example of how this formula helps. So find Laplace transform of sine square t function. So if you want to find the Laplace transform of this function, what is this function? This function is ft is equals to sine square t. We want to find its Laplace transform. So we know that if ft is this function, its derivative will be 2 sine t into cos t, that is 2 sine theta cos theta is sine 2 theta. So it will become sine 2t. So we know the function and its derivative. Now, if we want to use the first derivative formula, that is this one, then we need to know the value of the function at 0. Right. So what is the value of the function at 0? So in the function we substitute t is equals to 0. So that is sine square 0, which is 0. So what does this gives? This gives, therefore, by the above formula. So let us simply apply the formula. We get Laplace transform of the derivative, that is s times Laplace transform of f minus f naught. Right. So let us just substitute everything here. So that means Laplace transform of derivative. What is derivative? Derivative is sine 2t. Right. That is s times Laplace transform of f. So we don't know what is Laplace transform of sine square t. That is what we are finding. And f0 is 0. Right. But now you can see that we don't know this Laplace, but we know the Laplace transform of sine 2t function. Right. So that we can use here. So that means Laplace transform of sine square t function is nothing but 1 divided by s times Laplace transform of sine 2t. So since we are dividing by s, we can assume s is greater than 0. Okay. And now we know that Laplace transform of sine 2t is nothing but 2 divided by s square plus 2 square. Right. Why? Because Laplace transform of sine at is a divided by s square plus a square. So if we substitute a equals to 2, we get Laplace transform of sine 2t, that is 2 divided by s square plus 2 square, and 2 square is 4. So let us write down that directly. Okay, so this is the Laplace transform of sine square t. So what is Laplace transform of sine square t? Laplace transform of sine square t is 1 divided by s, 2 divided by s square plus 4. Right. So in Laplace transform, as in the other case also, we can you may say that this is a sine squared t function, so we can also convert it into some other geometric trigonometric formula also we can use. So that is correct. This example can be solved by some other way also, right? Using cos formula also, cosine t, but answer you will get is same. So you can check that later on. Okay, so this is the example of the derivative. Now let us take one initial value problem, and uh, if we can solve that using the Laplace transform, how to solve that? So solve the IVP, that is y double dash plus 4y is equals to 4x with initial values. So initial value here given is value at 0 is 1, value of the derivative at 0 is 5. So solve this initial value problem using the Laplace transform. So we know what is the Laplace transform of the derivative, right? And we know what is the Laplace transform of t power n function. So that we will use here. So first thing, observe that here our function is a function of x variable, right? Y is a function of x variable. But usually when we discuss Laplace transform, we are considering the function which is a function of t variable, right? So if function is function of t variable, then the Laplace transform of t power n is n factorial divided by s power n plus 1, right? So if we write the same formula in terms of function of x, then this gives Laplace transform of x power n is n factorial divided by s power n plus 1, right? So whenever the function is function of x, we use this formula. Whenever the function is function of t, we shall use this formula. So let us apply the Laplace transform on the differential equation. We know that the Laplace transform is defined using the integral, and therefore the Laplace transform is a linear function, right? So that's why we are calling it transform. It's a linear function. So that means whenever we apply Laplace transform on the equation, both the sides, we get this equation, right? So we have applied Laplace transform on the differential equation, we got this equation. Then Laplace transform is linear function. That means we get Laplace transform of the first term plus Laplace transform of the second term, right? And then we know that it is linear, so it preserves the scalar also, right? So here we are using Laplace transform is a linear function. So now we know that Laplace transform of the second derivative. What is Laplace transform of second derivative? That is using these functions. So instead of f, we have y double dash. So that means we have s square Laplace of y minus s times y0 minus y dash 0. So let us substitute it there. So what we will get is the Laplace transform of y dash is s square Laplace transform of y minus s times value of y at 0 minus y dash 0, right? So this term has become this term now, plus 4 times Laplace of y as it is. On the right side we have 4 times Laplace of x. So x means we have Laplace of t basically, right? And we know Laplace of t is t power n is n factorial divided by s power n plus 1. So that means we have 1 divided by n is 1 here because Laplace of t, so it is 1 by s square because 1 factorial is 1, right? So this equation we got, and then we know the initial values, right? That is given in the example. Y0 is 1 and y dash 0 is 5. So let us substitute the initial value now. So what we get is s square Laplace of y minus s times y0 is 1 minus y dash 0 is 5 plus 4 times Laplace of y is equals to 4 divided by s square, right? So s times 1 is s. So let us just remove this 1, right? So we get this formula. Now you can see that this formula has two terms involving Laplace of y. So that we can take common, and other term we can take on the other side. So we get s square plus 4 times Laplace of y, that is these two terms. The other term is 4 by s square minus s, and 5 we can take on the other side. So we get plus s plus 5. The sign will change, right? And now we can convert the equation in terms of Laplace of y. So Laplace of y is what? That is 1 divided by s square plus 4, right, times 4 by s square plus s plus 5. So now if you see this formula, we know that if s divided by s square plus 4, then that is in terms of Laplace transform of the cosine function, right? Similarly, some constant number divided by s square plus 4, that is in terms of Laplace transform of sine 80 function, because sine 80 is Laplace transform of sine 80 is a divided by s square plus a square. So that means we can use those formula and find out what is y, right? So now we know what is Laplace of y. We need to find what is y. So that is where this inverse symbol will be useful. So if you know the function in terms of s, we can find function in terms of t, right? So if we have s function in terms of s divided by s a square plus s square, we can use this formula and we get cosine t, right, depending on this a square term. Similarly, sine also we can use. So this sine formula also we can use. Okay, so let us just write down this again. So what we got is Laplace transform of y is nothing but 4 divided by s square times, in the denominator we have s square plus 4, right? That is the first term. The second term is s divided by s square plus 4. The next term is 5 divided by s square plus 4. So now what we'll do, we will take the inverse Laplace transform. So if we apply inverse Laplace transform, L inverse L will be y, right? And on the other side, when we apply L inverse, Laplace transform is a linear function. The same way, Laplace inverse is also linear function. So we get Laplace inverse of the first term plus Laplace inverse of the second term plus Laplace inverse of the last term, right? So we are using here Laplace transform is linear, so its inverse function is also linear transformation. Okay, so yeah, so now what can we say about this term? This we know that this here we can apply the cosine Laplace formula. Here we can apply the sine Laplace formula, but here we don't know what to apply. So what we can do is we can separate that term in two parts, right? So so we can use the fraction form, so that we can write as 1 upon a square minus 1 upon a square plus 4, right? So whenever we take LCM, we get the denominator is a square times a square plus 4, and numerator is a square plus 4 minus a square, that will be 4, right? And the other term as it is, okay. So now we know the Laplace transform of t power n. Laplace transform of t power n is n factorial divided by s raised to n plus 1. So that means Laplace inverse of 1 divided by s power n plus 1. So in that case, n factorial will go in the denominator, right? So here the first term is of that form, the Laplace of 1 upon s square. So that will give us t, right? So what is Laplace transform of t? That is 1 factorial divided by s square. So that we use here. So which function is Laplace transform 1 upon s square plus 4? So
That's fine. If we multiply 2,
correct, correct, you are right. So the main step is we need to multiply and divide by 2. So that means it will be half time Laplace inverse of 2 divided by s square plus 4. Correct. And then we know that yeah. So let us write the one more step. So this we already know, s divided by s square plus 4, and the last term is again we need to convert into sine. So we will have 5 by 2 L inverse 2 divided by s square plus 4. Correct. So now we can simply write down this is nothing but sine 80, where a is 2. Similarly, this term is cosine.
for 2x.
Pardon? Yes, you are right.
X.
So we are considering as a function of x. Yes. Yeah. So that should be x. And the last term will be again sine function. Yes. So now we got this term as a we found yx. Yx is this function, and in fact we can simplify this function further because there are two sine terms. So essentially we get 2 sine x, sine 2x. Yes, so this is the solution. So we have discussed 2 or 3 methods to solve the second order differential equation. So this is a second order differential equation with the initial values, right? And actually it is a non-homogeneous equation with the constant coefficients. So we need to solve the other method which we discuss is a variation of parameter method, right? Because it is a non-homogeneous equation with constant coefficients, second order linear with constant coefficients. But here, if we solve it with Laplace, then we don't need those methods. We can directly apply the Laplace transform of derivative and Laplace transform of sine and cosine term. Okay, so this is the one problem which I wanted to discuss regarding the Laplace transform of the initial value problem. Let us discuss one small result regarding the scaling of Laplace transform. So whenever we have positive number a, and if we want to find Laplace transform of f of a times t, then that will be nothing but 1 divided by a times Laplace transform of s by e. Laplace transform of f when substituted s by a instead of s. So proof is very simple. Laplace of f a t is nothing but 0 to infinity. By definition, it is this integral, and then we can change the variable. Just substitute at is equals to some variable. Let us say it is x, and a is positive. That means a dt is dx, and since a is positive, limit will be same, 0 to infinity. So if you substitute this, we get the Laplace transform of f a t equals integral 0 to infinity e power minus sx by a, right? Because t is x divided by a, fx, and then dt is dx by a. Because a is positive, we can divide by a, and this we can take 1 by a outside. It will be 0 to infinity e power minus s x by a, right? Fx dx. Yeah, so yeah, so we need to combine a with s here, right? Okay. So again, if you want, we can write instead of xt. So essentially, what we get is 1 upon a times Laplace transform of the function f, but here s is changed by minus, s is changed by s divided by a, right? So we can verify this theorem using sin at formula. So we know the sin at formula and sin t formula. So simple example is Laplace transform of sin 2t. So here basically we are taking a is equals to 2. So by this formula, it should be 1 divided by 2 Laplace transform of s by 2, right? What does that means? That means, yeah, so what is fs here? Fs is Laplace transform of sin t, right? So when we substitute s by 2 here, what we get is, what is Laplace transform of sin t? That is 1 divided by s square plus 1, right? And in that we substitute s by 2. So that means we get 1 divided by 2, 1 upon s by 2 square plus 1, right? So now in the denominator we have s square by 4 plus 1. So that will be s square plus 4. In the numerator we have 4, and 4 will cancel out with 2. So essentially we get 2 divided by s square plus 4, right? So using Laplace transform of sin t, we derive Laplace transform of sin 2t. In general, we can do the same for the Laplace transform of sin 80. So sin 2t formula we already know. Directly we have derived, but we are also getting by application of this theorem. Okay, so I think this should be enough for today lecture. We have some more methods that we will be discussing in